Good morning, everybody. Welcome to the 35th Leonard A. Ford Lectureship. I am Dr. Daniel Swart. I'm the chair of the Department of Biochemistry, Chemistry, and Geology. Our speaker today is Dr. Nick Riley. He's an assistant professor in the Department of Chemistry at the University of Washington. Dr. Riley earned his BS in chemistry from the University of South Carolina. He then moved to the University of Wisconsin-Madison, where he earned his PhD, studying with Professor Josh Kuhn. He completed a postdoc with Professor Carolyn Bertozzi at Stanford University. His research group uses state-of-the-art mass spectrometry and chemical glycobiology to investigate glycoproteome regulation. Dr. Riley, welcome to the Minnesota State University Mankato.
Awesome. Thank you. Well, thank you so much for the introduction, the invitation to be here. It's a huge honor to be invited to a lectureship like this, so it's also very cool to see you all in the audience this morning. So thank you for all the above. I wanted to start with a brief show of hands. Who all has been to Seattle before? A few more than I expected, but that's awesome to hear. I would say consider this opening slide your official invitation to either come for the first time or come back, because this is a picture of my walk into work from my cell phone from our campus. So our building is just on the right side of that fountain right there. One reason it's an easy way to show off a bit of Seattle, but also it's a great intro into thinking about analytical measurements and the tools we use to study the world around us. Because if you have been to Seattle and you've been on UW's campus before, you might know that there's one really big thing that we can't see in this picture. And maybe if I chose another picture from my phone on a different day, maybe like this one, and hopefully you can see that and with the lighting. But there's a giant mountain that's right behind where that fountain is. And it's a pretty hard feature to miss if it's the right timing, the right day, the right conditions. And I like to think of this when we think of how we make measurements about any system we want to study. Are we looking in the right way with the right tools at the right time? I also just have a lot of these pictures on my phone, so it's easy to pull these up and enjoy some of the good views we've had. I'll also say, I have another picture too, that this beautiful area, we like to make a land acknowledgement statement at UW. We have a lot of native tribes whose land that we occupy. And so another beautiful picture from a walk-in this morning, and I'd like to acknowledge these peoples that are in Seattle. And then if you'll humor me, a lot of my friends or colleagues, when they've seen this, are like, you're only showing pictures of Seattle when it's beautiful. Surely it's not like this all the time. And I say, I see spring, summer, fall, and winter. It looks great every day. Now, of course, it's not quite true, but just to make sure that we can exhaust the reason I take all these pictures, I have to at least include a few more. And if you'll humor me, one last slide. I've been using this one in the past few months as kind of a statement of solidarity. We're in a time where higher education and science are kind of being divested in the public sphere. And so it's a statement just to say with people that are interested in continuing to push forward with science and higher education, to keep fighting the good fight and to keep bettering ourselves that way. And one of the reasons I like to make this statement is because the reason we want to keep funding going, the reason we want to keep pushing the edge of knowledge and training people is because the next generation of scientists are incredibly important for the next generation of biotechnology and other technologies that will come out of the US scientific enterprise. So I like to then lead directly into the people. The reason that I put that statement on that slide is my research group. So this is the team that I lead that are full of graduate students, postdoctoral scholars, and undergraduate students as well. We'll return to this slide at the end, but I always like to show them first because it's about the people first and foremost, science second. From here, I won't talk a ton about data today, because I want to talk about big picture concepts. But normally when I give talks, these are the folks that are doing all the cool work and experiments, and I just get to talk with them about what they see, suggest next experiments, but they get to do the fun stuff. So I like to highlight them as much as I can. Also, you heard a little bit in the intro about where I've been, but I like to also use this as a launching point for talking about my journey into science and how I got to the research that I'm interested in today. So again, I'm from Louisville, Kentucky, or Louisville. I say it like Louisvillians do. But I was born and raised in Louisville, and then went 8 hours away for undergrad to the University of South Carolina. So the Southeast was kind of the world I knew, and I decided to then move up here to the upper Midwest and enjoy some time in Wisconsin and Madison, and that's where I got my PhD, as you heard. And I thought a lot about method development, and analytical tools, and instrumentation there. So we're going to talk mostly about that today. But then that tool set that I worked on ended up being really useful for a cool class of biomolecules called glycoproteins. And we'll maybe towards the end of this get a bit into what glycoproteins are, but there will be direct references to the M&Ms that you now have in your hand and hopefully are enjoying before they melt in your hand. Or not in your hand, only in your mouth, right? But I moved to the West Coast to study those glycoproteins and worked in the Bertozzi group there before starting my group at University of Washington 2 years ago. So it's kind of the journey there. And I like to use this as a launching point too, because I think it's part of discussing paths you might be interested in thinking about science and what that could mean if you're interested in that for your future too. So I'll say as we're talking about this, it's very easy retrospectively to be like, look at this very clear path that I took. It was so obvious where I was going to go. Not true in any way, right? And also when you look at other folks, you're like, wow, how did they figure it out so early? It's so rare that that is the case. And so even as I tell you about how I got to where I am and the research I've been working on, it was not that straight path at the top. It was very much trying to figure out what the next step looks like, where do I want to go. So I hope that if that resonates with you too, it doesn't ever need to be a straight line. As long as you have a goal in mind, you can keep working towards it. So with that, let's focus in briefly on the first steps of this journey for me. So growing up in Kentucky, going to South Carolina, when I started there, I knew I wanted to be in the chemistry sphere. I knew that because crime scene investigation, CSI, started in 2000. I was in 5th grade, and that scared the life out of me to start because it was like dead bodies and stuff, but then I was like, wow, this is really cool. They're figuring out stuff with chemistry and other tools. Then I happened to enjoy my chemistry classes. And so as I was going into undergrad, I was thinking mostly about, well, could I do something like forensic science for my career, my life calling? But I think more broadly, if I had to zoom back out and look again retrospectively, it was more about solving and putting together puzzles. I really like questions where we know that there could be and should be an answer. We have no idea what that answer looks like yet. How can we use the tools that are in front of us to piece all that together? So that's one of the reasons that chemistry really called to me. At University of South Carolina, the research that I did was forensic analytical chemistry. And so what this looked like in the projects I worked on was looking at clothing fibers from crime scenes. And so of course we were creating fake crime scenes to start with, but the goal would be to apply this to very real world situations where you could take a single fiber you might find, extract dye from it, and then characterize all the molecules that were in that dye. And the goal would be, could you then be very precise about saying that this fiber was only in, because of the dyes that were on it, were only in batches sold at these locations at this time to help pinpoint maybe who might have been where at any given time. As it turns out, this whole cycle was a cool project to work on, but I kept asking questions to my advisors about only this, and they noticed. Like, you are only asking about how do we get, what does this arrow mean? How do we get data? And this data is really interesting. But you haven't really asked much about any of this stuff, and you haven't really asked about the crime scene. So maybe you should think a bit more about what these methods look like if you want to continue in the analytical sphere. And so what we were using was mass spectrometry, and we're going to talk a bit about that today. We were using a mass spectrometer called the triple quad. You can see here there are 3 quadrupoles, and so very aptly named instrument. But what I liked about it is that you could take an unknown, use this instrument to either measure intact species, or you could break those apart to figure out their pieces. And that really became the puzzle that I was drawn to even when studying chemistry in the first place. So as I was thinking about this, I had really important people in my academic career that pointed me this way. As I mentioned, I don't think I saw it, how interested I was in the instrumentation, until they mentioned it to me. So people like Dr. Morgan and Dr. Brewer and Dr. Chin were incredibly important in guiding me there, and that I was able to kind of listen to what they were saying. Because I think it was an interesting step for me that very much changed the trajectory of what I thought I was going to do with my life and my career. And so a reason I put this up is so we're at this stage now where I've been in Columbia, South Carolina for a few years. And I put this pie chart, because that was, estimating how I was dividing my time amongst things in undergrad. And if you wanted to guess which slice of that was science and research, it is not the one you might think. It's probably that one. I was doing so many interesting things. I was enjoying undergraduate work. I was trying to, I was playing sports. I was being in different social events. And so I wanted to highlight this too, that it wasn't like I had to lock in and be like, research is my life. That's what I want to do forever. but I tried a lot of different things and thought I wanted to go into a career maybe in higher education, student affairs, and other realms too. But because of my interest that came from this undergraduate research experience that I didn't spend all of my time doing, it kind of led to this thread of like, oh, this is cool and I want to think more about this in the next step. And so that's what led me then to move from my little corner of the Southeast up to Madison. And so there I focused in the Josh Kuhn's group a lot on the mass spectrometer itself. And so I wanted to spend a little bit of time talking about why I think mass specs are so cool, because I know before I had this research experience, I had mainly used them in like my organic chemistry lab, which is super useful to say, I have made this molecule, I can prove it because I have the right mass. Mass spectrometers are so much more than that. And so I often even talk to my faculty member organic colleagues and like, oh, mass spec, yeah, whatever, you can measure stuff. I'm like, no, it's an entire field of research. So I wanted to just talk a bit about mass spectrometers in the first place. Then we'll talk how we use them in the group to study biomolecules. The last thing I want to say is that there were a lot of directions I could go. This pie chart, I was doing a lot of different things. We had a great conversation at dinner last night, and this quote stuck with me. And it's that make a decision, and I'd say make an informed decision, parentheses there, but then make it the right decision. You could do a lot of different things, but when you choose, go do that and put yourself into it. And I could have probably done a lot of different career paths, but I'm very happy that I chose this one and made this the decision that worked the best for me. So that'd be one piece of advice I have for you all as you think about next steps too. But okay, when we think about how a mass spectrometer works and why it can be such a valuable tool, I want you to imagine what you do anytime in the real world, not necessarily just in the lab, like when you're trying to discover or understand something. If it's something new you've never seen, you might pick it up, turn it around, feel how heavy it is. If it looks like food, you might smell it or taste it. You know, there's all sorts of ways that we interact with unknowns in our day-to-day lives. And there's a great cartoon that I think a lot of people may have seen before, but if you haven't, it's a wonderful one, because this is effectively what scientists are doing on their day-to-day research, is that we're trying to study some phenomenon, but we're blindfolded. We don't know the answer, and we're only looking with our one perspective that we have. So if you're looking at an elephant and you're blindfolded and you only felt its trunk, you might think, well, I know nothing else about this organism. It must be a snake, or it must be a spear, or a rope, or whatever it might be. And so we're going to talk exclusively about mass spec today, but I also wanted to make sure I highlight that in the analytical and bioanalytical sphere, there's spectroscopy, there's electrochem, there's so much more than just mass spec. So this is kind of my way to say, like, we are just one of these blindfolded scientists feeling around in the dark as well. I will say, knowing the mass of something is super informative. You can know a lot about a substance if you know what its components, what it weighs. And that's because we know things are composed of these elements that have distinct molecular weights. And so when you put things together, they're often combinations. You can say, I know what this species is because I can measure its mass. And so if you think of something like this would be a mass spectrum of a peptide called glucagon. And just by measuring its intact mass, we get this mass spectrum, and we're going to talk more about what a mass spectrum looks like and how this came about. But you can see now that we have a chemical formula that we can attribute to this mass. And this now is a sequence that we can piece together of different amino acids. And so the things that I really want you to take away from this slide, though, are that what a mass spectrum is, it's a mass to charge measurement. And we're going to talk about that mass to charge here in a second. And then an intensity. And the intensity part we're not going to focus as much on, but more, how does this mass to charge ratio give us information? And so when we think about what a mass spectrometer is doing at its core, we're taking an ion, and I made sure to bold and underline this so you guys can see it, because in mass spectrometry, we have to have charged particles. If it doesn't have a charge, you can't control it at the mass spectrometer. And so an entire Nobel Prize was awarded to 2 different teams that figured out how to put charges on molecules. And I teach this topic, and it's several lectures long, so we don't have time to dive into the details. But an important part of this is that we have either a positive or a negative charge. And what that means is we can put electric fields on pieces of metal. It gets a bit more refined than that, but in the most simple sense, it's what it is. And we can control the trajectory of how ions move in a system just from those electric fields. At the end, we put a detector, and what we detect is based on the electric fields that we applied. which is based on the mass to charge of the molecule. So we can detect things when we know and attribute that to its mass to charge. And we won't definitely dive into this, but I want to just say, if you're interested in this, it sounds kind of cool. We can absolutely describe these mathematically, right? We have these solutions to differential equations. These equations are called the Matteau equations. And these basically let us describe motions of ions through these fields by the number of charges, which we represent in these equations with an E in its mass. So we already have its mass to charge ratio. Here's just the inverse. And then we're looking at DC, direct current, and AC, alternating current voltages. So we can describe all of this motion just by knowing a few parameters that way. Again, we won't dive into that yet, but if you want to learn more, it's a very cool space. It's a bit of a mix of chemistry and physics, too, which I find very interesting. When we think about now these metal plates and how they're controlling ions, there's several different types of mass analyzers, or instruments that can control ions based on this mass to charge value. And so the ones that you may have heard about before, we already mentioned a triple quad, which has a quadrupole mass filter in it. Things like time of flight are often very useful in a lot of different applications. Ion traps and orbit traps tend to be a bit more nuanced in kind of the omics and biomolecule space, but you may have heard of all of these before. And I think time of flight is probably the easiest conceptually to think about of how this generates a mass to charge spectrum. So this is, we'll keep replaying, but we see that we're creating ions in this first part. Again, we're going to skip over the details of that. But effectively, we're ionizing molecules, and they're entering the mass spectrometer. And then we're going to push ions right here with the same kinetic energy. But you can see these different ions are different sizes, which we're using as a proxy for different mass to charge or mass values. And so when we push these with the same kinetic energy, like if you were to push a ping pong ball and a bowling ball with the same exact force, which one would go further or go faster? We basically can use that as a metric for their mass to charge. So the lighter mass to charge ions arrive at our detector first, our heavier ones arrive last. And so you can see then we generate a mass spectrum based on when they arrive, and that is why this instrument is called a time of flight. They're directly related to its mass to charge. Again, we can describe this mathematically. We won't worry about those details right now, but hopefully a straightforward way to see how we can use manipulations by the voltage we apply with this push to the measurement that we make. Another one that we use all the time, and you may have used in labs as well, is this quadrupole mass filter. And I find these incredibly cool. And so just to kind of talk about what a quadrupole is, again, this will be no math, just kind of hopefully a descriptive idea. We basically have these 4 rods, the quadrupole, which it's technically not called the quadrupole because of 4 rods, but because it uses a quadrupolar field. But if it helps you to remember quadrupole has 4 rods, that works too. We're going to apply different voltages to each rod, and we're basically going to use different versions. You can see these AC voltages are offset, so when this one is lowest, this one is highest. And what that does is we basically are having either positive or negative charges on these opposing sets of poles. And so you can see the red and blue is representing there. Maybe if I go back and do it one more time, that's whether those are positive or negative, and it's switching between red and then blue and then red and then blue. What that allows us to do is once an ion is in this device, as it's alternating around, it's getting pushed or pulled away by a negative or positive charge. And it keeps also oscillating negative, positive, negative, positive. So the ion's like, I want to be there, I don't want to be there. And that keeps it in this trajectory, this kind of corkscrew shape. And how we've applied those voltages tells us the ion will either stay within the device or it will have too much energy and get kicked out. And that ability to stay within or get kicked out is all based on its mass to charge. And so it's a little blurrier than I was hoping, but this is kind of the description of how you can use a quadrupole is you have some ability to create ions. Again, skipping over the details, but we have had to make ions. They're going to travel down this quadrupole device to a detector. We have these poles that are alternating. And so here, the blue trace, we've set the voltages so it can make it. We've set the voltages so this black one has a different mass to charge value, crashes out, and doesn't make it to the detector. And this is how we can use measurements that are, again, based on mass to charge values. And so what this looks like, again, details I don't want you to focus on. I want you to focus on big picture idea of let's say that all of these ions, they have 5 different ions, they have different mass to charge values. They're all entering our mass spectrometer at once. How do we pick just one and say, I want to only analyze ion that has this given mass to charge. Well, what we do is we set combinations of these direct current and alternating current voltages. And we haven't talked at all about these stability diagrams. So basically, if that intersection occurs within the triangle of a given color, that means that that ion is stable. If that intersection occurs outside, so you can see this intersection's outside the red and outside the green, those are not stable. And so what ends up happening, if you set your voltages with this combination, you only keep that orange ion. That's the way you've used the mass spectrometer to basically pick out and say, only give me this one species. And what a cool way to have selectivity in the gas phase. I'll give you a few more examples so you can see some ideas here. If we were to switch these around and now have a combination of alternating current and direct current that is here, this one, that intersection is only inside that blue triangle. So only the blue ion has made it to our detector. We don't have to just select one ion. We could choose combinations where we have multiple things that have stable trajectories that come through. So you have all sorts of ability to tune this, and this instrument becomes incredibly versatile in measuring all types of molecules that you may want. I'll give you one more example here where we can basically have what we call an all-pass filter, where we've just turned off the DC voltage, set it to 0, and chosen some AC or RF voltage that allows all of the ions to make it through. So we have so much versatility with this. And so what that ends up making, or what you end up with after you've used a quadrupole to do mass spectrometry, is you have this mass spectrum. And again, this comes back to a mass to charge measurement. At the end of the day, we want to know what is the mass, because that tells us the identity of what we're trying to study. And so here we have two species, and in this case, we're talking about peptides. So we're going to close the talk with the biomolecules again, so we'll talk more about peptides. But here we have two different species. And what we can use is these isotope patterns that allow us to calculate a charge. And if we know a mass to charge value and a charge, or a Z, then we can calculate an M, or a mass. And so here, the isotope pattern that we see tells us that we have species that the mass difference between these, the physical mass difference, is a neutron. So we have naturally occurring isotopes like heavy carbon, deuterium. And so those naturally occurring isotopes mean that we see some that have no heavy atoms. Some molecules of this peptide had one heavy atom or two heavy atoms. And we know, again, that the mass difference is 1 between each of these peaks. And if we measure the mass to charge difference, we see that that's 0.3. And you can see that that repeats effectively across here. And what that allows us to do is say we know that the mass difference is 1 Dalton, and we can calculate that our charge then equals 3. This gives us a lot of power, because now we say, I know the mass to charge, I know the charge. I can come back here and make a calculation on mass. You can do this for peptide 2. I'll just show you really quickly. This one, instead of being a +3, anyone can see it's 0.28 to 0.78. So that's going to be a delta of 0.5, which gives us a charge state 2. So now we can say, well, which peptide do we think is heavier? If you were just looking at a mass spectrum and didn't know charge, you might say, well, this is a lower mass to charge value, so this must be a lighter peptide. But it turns out the mass is going to be the mass to charge value times the charge. And it turns out that that peptide, the one at 500 mass to charge, is heavier than the one that's at 505. But this now is a direct way for us to convert information about the measurements we make to the molecules we want to understand. I'll say that modern instruments are not just a single quadrupole. They staple together and fasten together all of these different types of mass analyzers. So this would be one that we have in my research group, where we have a quadrupole, we have an ion trap, and we have this Orbitrap, which is a very useful, high-resolution, fancy new version of mass analyzers. But I say this because these are the types of instruments, like once you understand basic principles, you can learn how to couple the analytical properties of these different analyzers together and get really sensitive measurements to measure things in clinics or in environmental samples or whatever it might be. And so the question you're probably asking is like, all right, cool. Mass spectrometer, we get it. It measures ions, we can get a mass to charge value, it can let us calculate the mass. How does this relate to any biomolecular measurement or studying peptides or proteins, whatever it might be? And so these are examples of just a few different images of cells, or this would be a painting, artist rendition of all the different biomolecules that are in living systems, and they're very complicated. And so clearly we need tools that can measure all different types of molecules that way. And so something that's hopefully somewhat familiar to most folks is that we have different types of building blocks for these biomolecules: lipids, nucleic acids, carbohydrates, and proteins. And for the most part, nucleic acids do not use mass spec. There's been a revolution that happened in the 90s, 2000s, and 2010s of using we call next-gen sequencing, tools that don't need mass spectrometry to measure nucleic acids. And that's because of a lot of really beneficial properties in nucleic acids. They can be amplified. They can be like all sorts of ways we can control them that don't need mass spec. But the other molecules, pretty much all of them, rely on some type of mass spectrometry in their workflow to understand how all of these are operating in really complex systems. So my graduate work focused mainly on proteins, and then I got to this carbohydrate world. So we're going to spend our last minute of time thinking about how mass spec can be used to measure those molecules. And I like this quote, came from a paper a few years ago, and depending on the audience, it can be somewhat controversial, because basically a lot of folks that are studying the molecular biology of living systems will use transcriptomics or genomics because it is such a valuable and widespread tool set. The challenge is, though, that the genome and the transcriptome are like blueprints. They tell you what a cell could be doing, but the actual effector molecules, things that do the work in cells, are almost exclusively on the proteome and metabolome side. Metabolome can mean lipids, sugars, all sorts of different versions of metabolites. But we have to be able to study these molecules, and that's where the idea of building an entire research program about how to get better at measuring these molecules comes from. And so this is an entire industry of sorts in the US and across the globe, how to get better at measuring these molecules. And so with the general central dogma you likely have heard of before, we think of DNA to RNA to protein, and again, this being the effector molecule, and a lot of measurements that are happening here. And for a long time, one assumption was that the number of DNA molecules would be roughly equivalent to the number of RNA molecules, roughly equivalent to the number of protein molecules. And we know that it's much more complex than that. And so there's all sorts of layers of regulation that happen here. And at the end of the day, what this translates to is DNA, we know we have roughly 20,000 genes, 25,000 genes in the human genome. When you think about RNA, it's the like transcriptomic level, you end up multiplying that by some fold. But when you think about the versions of proteins that come from all these layers of regulation, you end up having many, many more types and complexities of molecules. This is where the analytical chemistry and the science comes in of how do we get better, faster, more sensitive at measuring this in really complex systems. So one other demonstration of this idea is, for a long time we thought there'd be one gene, one molecule. But we know now that a gene can make two different versions of an RNA molecule, and those can make different protein sequences. On top of that, proteins can be modified chemically with what we call post-translational modifications. It means they've already been translated from transcript to protein, and now they get some other chemical modification. On top of that, you can have different ways that the genome gets modified in other ways too. So there's a huge amount of diversity that comes from this. But at the end of the day, we are most interested in what we end up with. The term that we have chosen for this collection of all these modified forms is called proteoforms. And these are the functional units. These are the things that are actually doing the work. And the next slide kind of shows a few different disease states that you can highlight where the idea of proteoforms or these modifications really matter. And so we won't go through the whole list, but if we even think about something like neurodegeneration or Alzheimer's disease, we know that molecules like tau can get highly phosphorylated, which means phosphate groups get stuck to different side chains on the protein. And once that's highly phosphorylated, it completely changes how it functions. And so if you're measuring tau at a transcript or genome level, you say tau is present, but you don't know if tau is phosphorylated or to what degree it might be. And so that's the layer of information we have to capture, where mass spec really excels at doing this. And so this comes to the workflow that my lab uses all the time, every day. And so we're trying to study really complex and dynamic systems. We think a lot about human and mammalian systems to think about cancer and other disease states. And we interact with, and we have this conversation with, how do we prepare samples and get them ready for a liquid chromatography mass spectrometry experiment. And how do we operate the instrument? And once we have data, how do we translate that into information and knowledge? So there's a whole suite of technologies that work together here to answer some of these questions. And just to give you a quick insight into what the mass spec is doing, and we can talk back and go like why we need to understand how the instrument operates, is when we talked about that triple quad, we can do a situation where we have an intact mass measurement. So what we call this the MS1. These are all the peptides that are entering into the instrument at one given moment. We've measured that they're present. And I told you earlier that mass can tell you the identity of a species. And I kind of lied, because there's actually a lot of overlap in the human proteome that one mass could be represented by multiple different peptide sequences. So just knowing the single mass itself doesn't tell you everything you need. So we have to break it apart. And when we see the pieces, we can then say, I know that the pieces match up to this sequence and not to the other sequence. And so we do this often with collisions. So inside the mass spectrometer, we'll have what we call the precursor ion, or we've selected this one ion with our quadrupole. So again, we're only letting that one ion come through. We break it apart by just smashing it into some gas molecules inside of the mass spectrometer. And then we can measure the masses of the fragments using the same exact principles that we've talked about already. And so we call this spectrum the MS2. And then these are basically ladders of amino acids that tell us the sequence of what that molecule was. So it gives us a lot of information, and we can do this on the time scale of milliseconds. So we often, let's say we do an hour-long analysis of a complex sample, we might collect 100,000 MS2 scans. So it's a huge, big data type of experiment. So it's really a cool challenge, not only in how do you collect these to be the most informative, but how do you then have informatic tools on the back end to translate all of that information into what the proteome of that sample would look like. So I just mentioned, too, we kind of talked about the triple quad. It's certainly not the only instrument that's used to do this, but it's a really easy translation to say we do that selection, so only one mass gets through the quadrupole 1. This quadrupole has the gas in it. So we've pumped in some gas so that there's enough gas background for it. As molecules come in with kinetic energy, they hit it and fall apart. And then we can measure the masses of the fragments using that third quadrupole. And that's why triple quads are such a valuable instrument platform. When it comes to sequencing, again, a lot of detail here that you don't need to focus on, but big picture ideas. These are all the amino acids, the 20 common ones we have in humans. And this is a representation of a 4 amino acid peptide. We have an N-terminus of our peptide and a C-terminus. That's basically just them put together. And I tried to highlight that we have R groups. And these R groups could be any of these amino acids, right? And we could measure an intact mass of this, and we could know that these R groups, if they're all histidine or some, we could imagine they could be any combination of those. We could measure the mass, but if we could break them apart, we could see a difference between what the fragment that had the R group 1 or R group 2 or R group 3, and that gives us the ability to sequence a peptide. Kind of give you an example, the weakest bonds in a peptide tend to be this peptide bond that connects. So here's amino acid 1, that NCC, that's the repeating unit for amino acid. Here's amino acid 2, NCC. The peptide bond is what's between them. And those cleave very easily. So when we hit molecules against background gas, we tend to fragment at that bond right there. And we have named these with letters and numbers. But basically, again, the detail here I don't want you to focus too much on, but to say that if we measure a mass of that fragment, we can then say that fragment represents amino acid 1. And the difference between the mass of B1 and B2 is going to be that amino acid. And it gives us our puzzle pieces that we then stitch back together to get what the sequence looks like. And I don't want to go too deep into so much that goes on, but an entire field of research is how do you effectively fragment these molecules to get information from them. And if molecules are modified, that changes how they fragment as well. And so there's all sorts of layers here, like we need to study the protein regulation, what versions of modifications they have, how do we use our instruments effectively to do this. And so I'll come back then to what I did in graduate school and say that I worked on this technique called electron transfer dissociation in Josh's lab. And I'll put 1 second back. This is one of the versions where you can use electrons instead of collisions to fragment a molecule, and it has a lot of benefits that really are useful for modified proteins and peptides. So my entire graduate career thought about this. What I think is a cool analogy to make is basically the mass spectrometer becomes your beaker, but instead of liquid that you're mixing and trying to figure out a reaction, it's now all gas phase. You're doing chemistry, but with ions, and you'll be able to control them very precisely based on these electric fields you're using. So you can say, I only want this one ion, which is really hard to do in liquid phase, right? Think about mixing things with beakers. How are you sure that the only molecule you have is that thing, there wasn't any contamination? Well, when you use a mass spectrometer in the gas phase, you can be very selective. You can also be very sensitive with the number of molecules you need to make these measurements. And so what electron transfer dissociation does, it basically is a way to say to your peptide, I'm going to throw you an electron. And if you guys have taken organic chemistry or inorganic chemistry now, you know that radical electrons don't tend to just stay put. And so when you do this reaction, this is what we call a radical reagent, and it transfers this radical to the peptide. And so then this generates a radically driven fragmentation process that will fragment peptides really reproducibly at one bond that generates the C and Z ions. So it's not quite the same bond we looked at earlier, but just one bond over. And then what you can see, this is a peptide here, and we've generated all of these fragment ions, and we can use them. So the difference between, let's say, for example, C7 and C8, we came up here, that would be the mass of an alanine. And then the difference between C8 and C9 would be the mass of a leucine. And so we can use this to then piece together and know exactly what that species was. And again, we're collecting tens to hundreds of thousands of these in a given experiment. So this gives us a lot of power to study proteins and biomolecules, especially in complex systems. One challenge, of course, is nothing's for free, is that there are two pathways that compete in this tossing of an electron, right? So a peptide catches an electron, what does it do next? Oftentimes, what you hope would happen is that you would fragment and generate these sequencing ions, things that tell you what the amino acid ladder would look like. Sometimes, though, based on the gas phase structure, so how the molecule looks inside the mass spectrometer, you can get what we call non-dissociative electron transfer, where you break that peptide bond, but imagine like a wet spaghetti noodle. If it's folded up on itself and you cut one side of it, it's still going to stick together. And that's what happens to peptides in the gas phase. They have this secondary structure, and they're stuck together. And so we actually don't see any ions that tell us about sequence. It just looks like the same intact mass that we started with, and that's not very helpful. So what we can do is try and disrupt that structure. So instead of your spaghetti noodle that's all laying on itself, what if you could stretch out your wet spaghetti noodle so when you cut it, it fell apart into two pieces? There's a lot of ways to approach this, and the way that I worked on in my graduate career was using infrared photons. So we shot a laser into the mass spec, which is pretty fun. And what we would do is basically heat up these ions. So instead of being with some kind of structure, as they got more heat, they'd elongate. And that allows us to then use this electron-based fragmentation really effectively to generate this pathway instead of that pathway. What does this look like? Well, I mentioned instrumentation. And so this is a picture of actual mass spectrometers that I worked on at Wisconsin. And so these are not small instruments, but you can see that these were far from commercial grade. They were ones that we had, as a lab, purchased, and then we were modifying and doing all sorts of fun stuff too. But I say this as we thought a lot about how mass spectrometers work and what you can do with them, but the actual research you could be doing is very much in the instrumentation space, or it could be on the more applied biology space too, of course. But this would be version 1 that is, again, not very user-friendly, wires everywhere. This is the laser itself. We had it firing and coming back to the back instrument that way. This was the upgraded version that I finished out my work on, where you have the laser stapled to the back, and a bit more controlled system coming into the instrument. It turned out, by doing all of this work, we could explore some really cool biomolecules. And so I worked on things that included how to modify the instrument, how to study these proteoforms, and also how to develop software. But the thing that really caught my attention was how to use these tools to study these modified protein sequences. And one that was very useful, or this combination of infrared photons and electrons work together with, it's called activated ion ETD, the one we mentioned. It's really, really good for these molecules called glycopeptides. And glyco is just the Greek prefix for sugar. And so what these are proteins and and modified peptide sequences like this that have these large carbohydrates that get stuck onto them. And this is a whole fascinating world. And this was a cool spot to be as a method developer. It's like, oh, these are really challenging for a lot of people to work on. Turns out this works really well. All these purple ions give us the sequence of the peptide. And then these star ions actually tell us how the glycan is put together. That's from a combination of the infrared photons and the electrons working together. So again, I knew nothing about glycobiology, nothing about glycoproteins. It was like, this seems like it could be useful. I started to read about it, and it turns out it's a very, very complicated world. But that is where I think I encourage you guys, if you see something that's hard or challenging, that's where opportunity is. And so that's what ultimately had me decide to move from, I'd basically known life either on the Mississippi or east of it, all the way to the West Coast. And I'll mention Carolyn. If you have heard her name before, it's likely because in 2022, she was a Nobel laureate in chemistry. And she's been well known for the better part of 30 years for her work in glycobiology. She's really been a pioneer in how to study the sugar-modified proteins. And so I was looking around and saying, I have this skill set now in mass spectrometry. I want to do something that really matters in the biological world, and I want to do something that's really hard, because I want to keep building better tools and technologies that way. So I ended up there in her group in the Bay Area. And so what are glycoproteins? What is this glyco world that we've kind of been alluding to? Well, there's a word in the title of this slide that I had no idea how to pronounce before I joined Carolyn's group. It's called the glycocalyx. Again, glyco being the Greek prefix for sugar, calyx being the Greek word for husk. So it really means sugary husk or sugar coating. And effectively every cell we've ever looked at that we know of has some version of this glycocalyx. And so this is a collection of all of these proteins and lipids and other things that are modified with these sugars and carbohydrates. And so that's where the M&Ms come in, is that just like M&Ms, you can think of our cells having somewhat of a sugar coating. The difference is that this sugar coating on our cells is not static. M&Ms, like the sugar coating doesn't change. But as we have cells transforming to different states, going under physiological changes from whatever, it might be from disease state to healthy state or vice versa, that fuzz that you see on the cell surface here, so this is a cell with then all these, the fuzz is all the glycans, that is actively regulated. And so we want to study what that is. It turns out they're very challenging molecules to capture. We can draw that fuzz with a bunch of cartoons, but again, the details here don't worry so much about. But more to say, this would be the cell membrane. And so all of this is the extracellular space, stuff outside of the cell. And these are all the different types of glycoconjugates, things that are modified with sugars. And these images, the shapes and colors, we lovingly refer to them as our Lucky Charms figures. But they are representing glycans, which are just these complex carbohydrates. And so each one of the shapes and colors means something. They're actually chemical structures of these glycans, but it's much easier to look at this and say equatorial versus axial, and like basically say yellow versus blue or something like that. But to show you, this is an example of this glycan has this chemical structure. And so you can imagine if this is now modifying a protein, it's going to dramatically change how that protein might function in a biological system. A really big analytical challenge is that there's so much heterogeneity. It's not like a protein has just one glycan. So we need tools that can rapidly and sensitively capture all of the different forms that are existing on these really interesting dynamic cell surfaces. And what I'll say is that there's a lot of function here that we don't have time to go to in this lecture, but I'll be also giving a talk tonight that we can talk more about this if you will be there. I think it'll also be recorded. But all of the changes that we know happen at the regulation of these cell surface glycoproteins drive all sorts of interesting things we want to know about disease states and how things are regulated. One that we think a lot about that we'll focus on the next slide is an interaction here where this is an immune cell, and this might be like a cancer cell. And so we'll think a bit about that here. But I wanted to show you this to imagine, this is how glycobiologists like to imagine the world, is that a lot of molecular biologists, biochemists think of their favorite protein in its sequence and its tertiary structure, how the protein looks. But oftentimes, especially extracellular and secreted proteins, are glycosylated and it gets completely ignored because it's such a hard modification to study. But if your protein, you think it looks like this, but it actually is supposed to look like that, you can imagine how much different that function will be. And so this is the world that we think about. How do we capture what this state looks like? So my last set of slides here is just to give you one teaser of why this is important. As a quick show of hands again, has anyone here heard of PD-L1 or PD-1 immunotherapy before? Not much. Okay, let me explain it very briefly then. The idea would be this is a cancer cell. This is an immune cell. Cancers will upregulate proteins on their cell surface so that they are now displaying things like this protein called PD-L1. And it's a way to hide from the immune system because immune cells have this receptor, and that receptor basically puts the brakes on. If it gets bound, it tells the immune cell, like, whoa, don't kill the cell you just interacted with because it's likely a self cell, like it's one of us. And so cancers will hide from the immune system by upregulating things like PD-L1. And all this intracellular machinery is basically what tells the immune cell to like put the brakes on. And this has been revolutionary. It's really in clinics, it started about 2010, 2012. In melanomas and blood cancers, it's truly saved a lot of lives. But a challenge is that it's effective in far less of half the people that get immunotherapy. What we are starting to appreciate is that there are other receptors on immune cells that instead of recognizing just proteins, they recognize specifically glycoproteins, the proteins that have these sugar modifications on them. The challenge is, though, is that we are beginning to appreciate it's not just any glycoprotein. It's very specific protein sequences modified with very specific types of sugars. But we don't know what they are. And this is where the analytical and the biology meet. We need better tools to study what glycoproteins are upregulated by cancer and which receptors on immune cells are they interacting with so that we can try and block that interaction, basically taking the brakes off of your immune system so that it can kill your cancer cell. So that's kind of the big picture. This is a really busy slide to say, like, when we think about what a research group looks like, we work on all sorts of methods, whether it's about how to enrich things from a complex mixture, how to get better with our mass spectrometer itself, or how to put pieces together in the biological sense. So we kind of have seen a snapshot of maybe the more instrument side and the chemistry side here. But I think as you're thinking about research, it's cool to put all these pieces together. You don't have to just have one narrow focus if you are interested in a lot. We didn't talk at all about clinics, but I'll say that mass spectrometers are everywhere in hospitals. So if that's a world that excites you, mass spec is absolutely critical to that type of research. And I'll also mention, if you're interested in the environmental side of chemistry, mass spectrometers are crucial in measuring anything from water purity and cleanliness to energy storage and all these types of things. So it's a very useful technology if it kind of has piqued any interest there. The last thing I'll say is this is a great image, I think, of for science. And so we can imagine that you're just trying stuff. You're figuring things out. It might blow up in your face the first time, hopefully not physically, actually, but just metaphorically. But then you think about it, and you figure it out again. And so the message I want to leave you with is about, if you're interested in the science world, this is a really great, quick, rapid set of slides that shows you, imagine that all of this is human knowledge. And as you go to elementary school, you learn a little bit. Through high school, you learn a little bit more. And right now, you're specializing in something that interests you. You're getting a little bit of a specialty with your bachelor's degree. If you want to continue in that world, you could do a master's, you could go straight to a PhD. What it means is to basically hone in that space and keep digging and keep building that expertise. And as you read more, you kind of come to, like, what do we currently know and what do we not know? And as you get to that interface, you kind of realize you're at this boundary of what we do understand. And you focus in, and you push. And this is what a PhD is. Figure out what don't we know, what do we need to know, how do we get there? And then at some point, you'll find out something new. That is what research is. That is the PhD. And so that dent in, like, the new knowledge is what you hope to create. And I'll say, when you're in the PhD, you are, like, so focused in. And so I also, if you're interested in the research world, to think, like, you can learn so much and be in this space, but to also remember there's a lot to figure out. And it's a cool world to interact with where you collaborate and learn from people that know about the whole sphere of knowledge that way. And so my ending here is there is space for everyone in science. There's space for you if you're interested in this, and it looks so different for everyone. And if you're interested in this, to keep pushing. And especially if you decide to pursue science, it's challenging, fails 90% of the time, but that's the fun, is putting the puzzle together. I have an acknowledgement slide that I got to share like basically a year ago where I just could list a lot of people. And so I wanted to just briefly put this in here to show that it takes a village, and it's definitely not an individual sport, so to speak. And so this is just a huge list of far from exhaustive, but people that have helped me. But this is truly my last slide to say research is a group and human endeavor, and it's really great to work with people. And so I encourage you, as you think if you want to do research, trying it out now is a good way to do it. But don't think you have to be all in. You're writing your own first author papers, all that. It doesn't mean that's the only way to success. And so if you want to talk more about that, I think we have some question and answer stuff coming up. But also, I think I'm around all day if you have more questions. But with that, I really appreciate your attention. And I hope that it was, got to learn a little bit about M&Ms, if nothing else. And yeah, thank you all very much. We have some microphones for questions if anyone has any.
Do you have time for maybe one or two quick questions?
If you didn't get M&Ms, make sure you grab them on the way out. How many people have used a mass spectrometer in a lab or something like that thus far? Great, okay. Hopefully they are now much cooler than you thought originally.
I know we're running out of time. We will close right now. Students are welcome, faculty are welcome. We will have an open session with Dr. Riley for the next 45 minutes. I know a number of you have got to get off to class, so please join me in thanking Dr. Riley one more time.
Thank you all.